Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
The person who makes windows.
University of Michigan at Ann Arbor, and he has training partners in the departments of information science and computer science. At the same time, he's the head of the computational linguistics SNGER group there, which consists of 10 students, 5 PhDs, 5 master's students, and he's been working, as the group says, at the border between computational linguistics and SNGER, making deep forays on both sides of the border. And today he's going to talk on words, links, and patterns. And a special note, he has an open slot from 5 p.m. to 6 p.m. If anybody here or anybody you know would like to talk to him, just send me an email and I'll arrange for a room where he can meet you or other people in this room. Thank you.
Thank you, Cipriano. Okay, so welcome everybody. It's a pleasure to be here. In fact, I was here for the faculty summit, which was a very nice experience to get a chance to meet with all those people that you have. So I've been traveling a lot in the last few months, going to ACL and SNGER and all kinds of conferences. Actually, I get a chance to give this talk in a couple of different places already. And one thing that happened is that it turns out to be a fairly long talk. So what I'm going to do is I will present one part of it, and I'll try to finish by like an hour, maybe less, like 50 minutes from now. And then I would like to do a little overview of other things that we do at Michigan. And at this point in time, if you want to stay and listen to that, I'll take another 10 minutes. Okay, so, sorry, Cipriano already went through this part. Okay, so I'm going to talk about text mining from the web. Many people would ask, what is text mining? I'm going to give you a nice definition in just a little bit of time. Let me first give you some introduction. Well, you know the web is very large. A nice soundbite is that it's right now 10 to the 10th power in terms of the number of nodes, and it is only surpassed by the human brain as the largest network out there. And at the current rate of growth, it will only take a couple of years to become the largest one. It is large, but it also, as I said, keeps growing very fast, and it is also multilingual. So it used to be the case that English sites were about 95% of the web, but now it's more like 50%, and at this rate, there will be a minority very soon. Another property of the web is that it changes a lot. There have been studies that show that many sites change every day, others change every month. And you have to be able to, for information retrieval purposes, to be able to model all those changes so that you don't get with an out-of-date view of the web. A few more properties. It is semi-structured. It has some nice structure in terms of hyperlinks, in terms of tables on pages, and so on. But it is mostly natural language, so you have to be able to deal with that. Obviously, sites are of an even importance. Even within the same site, within the same page, there may be some facts that are more important than others. For example, new summarization systems in general will take into account this fact by focusing on the more visible parts first, and then not bothering the user with the rest. And finally, the web has a fairly complex structure. You probably know Broder's model from a couple of years ago, where he showed that there's one component that is the giant connected component with pages that are linked to each other in a particular direction. So you can get in from one side and leave from the other side, but you cannot follow links the other way around. So what does this tell us? What it tells us is that to be able to process textual data at this scale, you have to have adequate representations. You cannot just have, for example, a connectivity matrix with all the, let's say, 1 billion times 1 billion pages. That would give you something that is too hard to process on any computational mechanism. So the definition of text mining that I'm going to be using is by analogy. Like on the SATs, you had those analogy questions, right? Remember? So what I'm going to use as text mining is to natural language processing the same as data mining is to database. So the idea is that the largest databases are things like call networks for call records of telephone companies, which record every conversation that has ever been made, where it came from, how long, and at what rate, and so on. But data mining systems only deal with finding interesting patterns. For example, that business people call during office hours and that other people call during the rest of the time. So the same way, you have natural language processing, which deals with arbitrary texts, sentences of different lengths, different languages. But you also have text mining, which uses natural language processing and statistical techniques to find interesting patterns in text. So for doing text mining, you need to have some structure. And it is not clear if the current natural language processing technology is adequate to do things at the scale of WebIR. Now, I understand that many people here know what natural language processing is about. I'm going to just list a few topics that NLP usually deals with. Things like relation extraction, text classification, machine translation, question answering. Many of those are actually active areas of research at Microsoft. So here's a list of the ones that we work on at Michigan. So things like summarization, information retrieval, machine translation, question answering, and so on. So natural language processing traditionally is considered to be very hard because you have a lot of word knowledge involved. Not only is it hard in terms of parsing and structure, you also have to be able to understand each sentence. I'll just give you one or two examples. This is a famous example from Bar Hillel from the mid-20th century. Just to give you motivation, how large is the pen? Who can tell me? What's your best guess? This big? Okay, if I change the order of the words here, I got to like the boxes in the pen. How large would the pen be in that case? It would be much larger, and suddenly you're going to switch to a totally different sense. Even though a pen has a very obvious sense of something this size, which is a writing instrument, the syntax of the sentence actually predicts which word sense you're going to use. So to be able to understand this by a computer is actually a fairly hard problem. Nobody has been able to do this. And here I have a little collection. You can write those down. I can post my notes later. Some really classic examples of interesting sentences that show why natural language is actually very hard. For example, every American has a mother, right? I mean, one mother per person. That's quite a lot of mothers. But if you change the sentence to be every American has a president, or something like that, then the exact same syntactic sentence has a very different meaning, even though the selection or restrictions on the word, on the object are pretty much the same. It's an animate object, a human being, and so on. And then some more interesting examples, like my favorite one here, which shows you how ambiguity can creep into natural language, and in this case for humorous purposes. So, traditional natural language processing deals with mostly sentences of this sort. So you have to be able to convert one of those sentences into a semantic representation, then do some reasoning, perhaps answer questions in some knowledge-based form. Recently, however, NLP has evolved. It has become a lot more multidisciplinary, a lot more statistical, well-founded mathematically, and scalable. And it turns out that those are important properties for porting natural language to a much larger scale. So, I have a little nice illustration here. If this is natural language processing, those 6 things here are areas of science that have in recent years, in some cases for longer, contributed to progress in natural language. And somebody will say, well, I don't understand. What has bioinformatics have to do with natural language processing? Well, I'll give you some idea. In bioinformatics, you have this idea of sequence alignment of, let's say, DNA sequences, where it turns out if you replace the vocabulary of amino acids or base pairs and so on with words, you can use the exact same algorithms and do some interesting natural language processing, for example, acquiring paraphrases or doing word sense disambiguation. From statistical mechanics, NLP has recently borrowed ideas like conditional random fields, maximum entropy models, and so on. From sociology, as you'll see in part of my talks, the concept of social networks has been shown to be quite applicable. From linear algebra, graph theory, you have ideas like, for example, eigenvector centrality, and so on. Now, on the other hand, natural language has also contributed a lot to other areas of science. In fact, bioinformatics is a recent addition to this list. I don't know if you're familiar with this, but one of the formalisms for parsing natural language processing, natural language sentences, is tree adjoining grammars. So tree adjoining grammars are a formalism that was developed a couple of dozen years ago. It's a slightly weaker than context-free grammars. It's within context-sensitive grammars, but it can very accurately represent human language, and it is also reasonably easy to parse, unlike context-sensitive parsing in general. So it turns out that people have been recently using the same formalism for parsing sequences of DNA, even though that idea originated in natural language processing. And then you see all those other areas where NLP has made an impact. So what I've been trying to do is, since it's very hard to process individual sentences and then scale up to the size of the web, because sentences don't have fairly regular structure, you cannot just have like a database, a single predicate with a fixed number of arguments, and then parse a sentence into that representation. What you have to be able to do is to look for ways that different sentences are similar to each other, and then find structure which takes, for example, parse trees to a different dimensionality. For example, by looking at sentences that come from different sources, for example, different paraphrases of the same fact from different sources, things that change over time, things that are in different languages, and so on. So this was my little introduction. I'm going to spend the next half an hour on part one of this talk, which is models of importance, and I'm going to talk about multi-document summarization in the context of information retrieval. And then, depending on time, I will quickly go through the rest of the talk and give you some ideas of some other interesting projects that we're involved with at Michigan. So those include things like evolving models of the web for information retrieval, a new method for text classification using graph-based representations, and so on. Okay, so the first thing that I'll talk about is multi-document summarization. So News in Essence is a system for multi-document summarization developed at Michigan. It's available at newsinessence.com. It's open source. It's based on a system that we have been developing over the last few years called MEAD. So MEAD is a salience-based extractive summarization system for multiple documents. It works in multiple languages as well. So it's based on the idea of centroid-based salience. So in centroid-based salience, what you want to do is find sentences that are more similar to the centroid of a document. And I'll give you a small illustration of how this works. So you have a vector space model where each sentence is represented by a certain dot in an n-dimensional space. Then you do some clustering, for example, using k-means, like in our case. And for each cluster, you compute the so-called centroid vector. So the centroid vector is something like a sentence which has fractional counts of words. And it is in the center of weight of the entire cluster. So once you do this, you can find those sentences within each cluster that are closest to the centroid. So in some sense, you're doing first story segmentation. So you have, for example, the what part and the where part and the when part all split into different clusters. And then from each of those clusters, you pick the sentences that contain the most representative words of the cluster. So this way, you get a consensus of what's most important. So this is a fairly popular system. It has been downloaded more than 1,000 times, and it has been used by several systems in the official evaluation of summarization systems called DUC, Document Understanding Conference, every year. So I'm going to show you now, just for an illustration, what we use MEAD for. So News in Essence, as I said, was the first news summarization system on the web. It was built in 2001, first shown in March 2001 at the HOT conference in San Diego. So here's what it looks like. So this is the front page of News in Essence. And you can see the distinct components. One is a current summary of one of the stories, which was selected by an algorithm. And then you have different groups of clusters. For example, recent user clusters, recent CIDR clusters. CIDR is one of the components of the system, and recent Google headlines. So from each of those groups, we find automatically clusters of related news articles, and we produce summaries of each of the clusters. So here's what it looks like. So this is an example of a set of the most recent user clusters. You can see the date and the time that they were created. Then you have the cited automatically created clusters and the ones that come from Google. And then for each cluster, we can see what documents it contains, where they came from, when they were published. And then here the user can specify what compression rate they want to use to produce a summary. And this is what you get, from like a 10% summary of this entire cluster. So the second part is, in addition to CIDR, are the user clusters. In that case, we let the user select most recent headlines posted from a whole bunch of different sources. And then if they click on the News in Essence button, we produce a user-centered summary, depending on the user model, depending on a particular compression rate, based on the preference of certain types of sources over others. And just to tell you how this works is we look at the story that the user specifies as the seed. We identify the most important keywords in that story, and we send them off to the search engine for those particular news sites. And then we get more stories that way. Then we cluster them again all together into the same cluster and filter out the things that are too different from the original story. So this is how, in this case, the user has created a new cluster. Swiss President calls for UN membership. And then the current cluster becomes the leading cluster that we show in the centroid, on the first page of the system. And so on. And then the user can also create new clusters based on see the URL from a totally different source, based on arbitrary query words, and then they can also get updates on their stories every 12 hours, every 2 hours, whatever they prefer. Okay, now let me tell you a little bit more about some recent additions to the system. So this is the way that the system looked a couple of years ago. Now, in the last 2 years, we have been adding some new technology to it. One of it has to deal with relationships between sentences. Okay, so let's look at this document here. Obviously, for good summarization, you want to be able to, your summary to contain answers to all those different questions. What happened, when, where, how many victims, and so on and so forth. It turns out that the answers to those questions actually change with time, and they change depending on the source quite a lot. For example, the answer to the question, how many people were killed in a particular plane crash, can have up to 50 or 60 different answers. I'll give you a more recent example. 2 or 3 days ago, there was a very bad disaster in a supermarket in Paraguay, in South America, where the doors were locked apparently, and there was a gas canister that exploded and many people were killed. Well, if you read the story over time, or you switch from one TV channel to another, you read a different news site, you'll hear many different accounts of the story. Maybe the gates were not locked, maybe they were, maybe different people say different things, maybe the total number of victims changes with time, maybe the exact time, the exact reason why this happened changes. So to be able to account for this sort of contradictions and similarities across different sources, we have introduced a concept called cross-document structure theory. So cross-document structure theory tries to take into account the discourse relations between sentences that come from different sources to produce better summaries. So by discourse relations, I talk about things like contradiction, refinement, background, and so on. So how many people here have heard of rhetorical structure theory, RST? Okay. So for those who haven't, RST was created about 30 years ago by Mann and Thompson, and the idea is that when you have a single writer, a single human writer create a story, they typically follow a particular plan. So for example, they want to achieve a certain effect on the audience, so they give a claim, then they give a justification for the claim, then perhaps they give examples of the main points, and so on. So there is inherently a discourse structure within a document. And the typical example is antithesis or elaboration. So those RST relations typically hold between 2 different textual units, which may or may not be adjacent. Now, in the case of multi-document summarization, you cannot have the same type of relations because there is no deliberate writing on the part of the creator of the story. So in that case, what we need to do is find pseudo-relations. So things that are relations as far as the reader is concerned, which were not intended to be so based on what the writer wanted to do. So here's what our CST relationship taxonomy looks like. So we have things like identity, which is when 2 sentences are exactly the same. This happens a lot because news stories tend to be reused like at different hours by the same news agency. But then you can have paraphrases. That's when different sources of information say something about the same event. Since the event is the same, then it's very likely that the account will be somehow similar. But you can also have more complicated relationships, such as subsumption, contradiction, and so on. So let me give you one example. In subsumption, you have two sentences, one of which contains all the information that the other one contains, plus some more. So in that case, if you're restricted to a summary consisting of a single sentence, then you would rather pick the one which has more information than the one that has less information. Now, there are other relationships that deal with anaphora. So if you have two sentences that are adjacent, the second one of which starts with a pronoun, for example, he said, then if you extract only that sentence in the summary, the one that starts with he, you're going to get some miscommunication because it may be the case that the previous sentence is not extracted. Instead, he appears to refer to a totally different antecedent. So in that case, you have a discourse relation between those two sentences. Now, the difference between the two classes of CST relationships is that one has a positive effect, and the other one has a negative effect. Here's what I mean. If you have one of the sentences in the anaphoric example included in the summary, you really want to include the other one as well, because otherwise the text will not be comprehensible. If you have, for example, subsumption, then if you include the longer of the two sentences, then you don't want to have the second one. So in one case, you have some sort of an inhibition between sentences. In the other case, you have some sort of positive feedback. So how do you use this in summarization? Well, here's how you do it. I have a very simple diagram here. Then I have an algorithm which I'm not going to describe in detail. Suppose this is a multi-document cluster. So this is one story, another story, a third story. And suppose that you just pick the most important sentences based on their centroid values. So you would pick, for example, those four circles that are in blue, because they're more similar to the respective centroids of the different clusters. In this case, what will happen is that you are now producing a summary that contains a single instance of a negative CST relationship. And all the possible candidates for positive CST relationships are not included in the summary. So you can now reformulate the summary by dropping some of those negative nodes and adding some positive nodes instead. So to do this, we have an algorithm which is described in the paper, which was a PPOI paper last year, but it's based on the idea of a CST connectivity, C equals -1. So C equals -1 is computed by adding together all the instances of a positive CST relationship and subtracting the number of negative. So in this case, the summary only contains a single negative CST relationship, therefore the CST connectivity is -1. And obviously the goal to produce summaries that have a better CST connectivity is very simple. What you can do is, you can add a node that would give you an extra positive CST relationship, and then you can remove a node that would get rid of one of the negative relationships. And then you would get a totally different summary with a CST connectivity score of +1. Okay, I'm going to talk about the evaluation at the end. So this is the basic idea. Now, next thing I'm going to talk about is a recent project, which was just presented a few days ago for the first time. Actually, I'll take this back. It was first presented at DUC in May, and we also presented it last week. So it's based on the idea of social networks. Now, how many people here know about social networks? Okay, just a few people. So a social network is a graph which has links between two nodes if those two people are connected by a certain relation. And typically this is about friends or people who publish papers in the same journal or play the same sport and so on. So they're induced by a relation which doesn't necessarily have to be symmetric. So the typical example would be Alison and Bill are friends. You would say that this is a symmetric relationship, but studies in sociology actually show that if you ask one person, are you friends with this other person, they will say yes, and then if you ask the other one, they might say no. So you may end up with a non-symmetric relationship. So one of the most important concepts in social networks is the idea of prestige of a node. Now this is one that many of you may have heard about from Google, the PageRank algorithm. So the way that PageRank works is that you have certain pages that have so many incoming links that come from good sites that by virtue of that they become more important themselves. But it turns out that there are really three different definitions of centrality in social networks. One is the so-called degree centrality, or number of friends. So this is just how many incoming links you have in the case of web IR. But you can also have this idea of geodesic centrality. So geodesic centrality is when you have two distinct communities, and I'm going to show this on the next slide. So two communities that are linked by a small number of nodes. For example, all the people who work at Microsoft, and then all the people who play soccer. And then there may be a couple of people who are in both communities. And if those people were to disappear from the network, you would have two totally disconnected communities. And obviously, the more likely it is that the graph will be disconnected after you leave, the higher your bridge centrality becomes. And finally, you have something called eigenvector centrality. So eigenvector centrality is what Google uses. So not only is it important, not only how many pages point to you, but how important each of them is. So I use an example like this. If, let's say, some Turing Award winner cites your paper, that somehow means more than if anybody else cites your paper. And why is that? Because the Turing Award winner is also somebody who's been cited many times. And this is a recursive relation. It's computed based on eigenvector centrality. Why is it called eigenvector centrality? Because you do a random walk on the connectivity graph, and then you can consider this as a stochastic Markov process with a stationary distribution. So you start from any place, and then you follow links based on the probability, based on the number of outgoing links from any page to another page. And then once you have done this until convergence, the probability that you would end up in any particular node of the graph is proportional to the eigenvector prestige of that particular node. And I mentioned that I have a little slide that shows you how, for example, the bridge centrality works. This is a nice slide that I got from Valdez Krebs. This is really interesting, especially in this year. Those are all the books that are against Bush and all the books that are for Bush that have been published over the last year. And you can see that what he did was he went to the Amazon website and he gave one of those books as query. And then he found what other people who have bought this book have also bought. Okay, so you can see that we have two fairly distinct communities here, right? One is people who only read this type of books, and one is the people who read that type of books. And then somehow in the middle you have this book, which I'm not sure which category it really belongs to, which people from both communities have read. So this would be a nice illustration of a high bridge centrality. But in terms of eigenvector centrality, it will be probably a node like this, or a node like this, which has a lot of incoming connections, and which would be the most central one. Okay, so I have two slides here, which I wanted to skip here. I just wanted to have more of a background on how to compute those. But what I want to get to really is how to use this in text summarization, which is what the main point of this talk is. So just to give an idea, again, the prestige vector is computed in an iterative mechanism by taking the initial assignment, which could be just 1 over n, where n is the number of nodes in the graph. And then you multiply this on the left by the transpose of the connectivity matrix, and you get essentially the probability that you would get from any place to another place in one step. If you do this 2 times, you get the probability that you'll get there in 2 steps, and so on. And it is guaranteed to converge because the matrix is stochastic and aperiodic, and a few other things are always the case. So let's go back now to summarization and see how this is related. Well, centrality in text summarization. Well, as I said at the beginning, to do summarization, particularly extractive summarization, what you want to find out is how salient any piece of text or any sentence might be. So there's several ways to do this. One is to use something called the sentence salience, which is based on the number of words that occur in the sentence that are similar to the entire document. You can also look at the centroid score, which is what I described earlier, but you can also look at other techniques for computing centrality. So you probably see where I'm heading. So let me give you an example. So this is a set of sentences from the same multi-document cluster, and you can see, if you can read those sentences, that they're fairly similar to each other, and yet they convey different ideas. So what you want to do here is to find essentially the most central sentence, the one that you would rather pick of those 11 to be the summary of the entire cluster. So this is the problem. How do you solve it? Okay, so I solve it. First, you compute the cosine centrality, the cosine similarity between each of those sentence pairs. Obviously, cosine is between 0 and 1, 1 meaning the two sentences have the same words, and 0 meaning that they have totally different words. And then its diagonal means, the diagonal here is always 1 because it's a symmetric relationship. And then you have high scores in certain cells, like 0.45 means that sentences 1 and 2 are fairly similar to each other. On the other hand, you have those zeros here, which indicate that sentences 1 and 11 are not so similar to each other. Now, if you turn this into a binary representation, saying that if the value Cij is higher than a certain threshold, then the new matrix is going to have a 1, and otherwise it will have a 0. you end up with a connectivity matrix that can be represented in the form of a graph, which is this. So if you pick your cosine threshold to be 0.3, then you're going to have a fairly disconnected sparse matrix. Like in this case, the only two sentence pairs that are so similar that they pass the 0.3 threshold. If you lower the threshold to 0.2, then you're going to have a little bit of structure. It becomes a little bit more apparent with the threshold that is lower. So even at t equals 0.2, you can probably observe that the sentence in the middle here somehow becomes the center of the whole graph. Not because it's drawn in the middle of the picture, it's because it has too many incoming connections or many links. And if you change the threshold to be lower at 0.01, it will turn out that this pattern is even more visible. So what I'm saying here is really this. Because this sentence is so similar to other sentences, which themselves are similar to the rest of the sentences in the cluster, thereby by virtue of that, this sentence becomes more important. And I'm going to pick that as my summary sentence. And what's really happening here is that the sentences are each voting for the most central sentence just by virtue of being similar to them, without any explicit hyperlinks. I'm creating the hyperlinks based on the similarity. Okay, so this is the idea. So again, we're doing summarization using this method, which is called cosine centrality. And we're going to pick this sentence because the page rank value, in a sense, of this sentence is going to be highest than any of the other ones. So let me show you what the actual values will look like. So we're going to compare the centroid, which is the best method before, like the intelligent baseline, and then the three new methods based on different thresholds for Lex page rank or for cosine centrality. So in the case of centroid, the sentence with the highest similarity to the centroid is this one, D5S2. And if you go back to the original sentences, you will notice that that sentence, in fact, is not as good as a summary sentence as the one that the cosine centrality method is going to pick. So D5S2 is the 10th and the second from the bottom, which talks about Blair and some meeting in the United Nations with the British Prime Minister, whereas most of the cluster is really about Iraq and the Prime Minister of Iraq and so on. Okay, so if you now do a Lex page rank with a threshold that is too high, you will get, because it's so disconnected, then the convergence will happen immediately. So you get 1/11 as the page rank prestige value for each of the sentences. That's why you have all those numbers exactly the same. But if you pick a more reasonable threshold, you get another sentence being on top. In this particular case, D4S1. Now somebody can ask me, well, how do you know where to pick the threshold? We have done studies, and we have shown that pretty much 0.1 is the best threshold that predicts the best summary sentences, and performance doesn't change dramatically if you go anywhere from 0.1 to 0.2, or if you go down to 0.05. If you go beyond that range, double or half, then your performance immediately drops dramatically. Okay, so now let's look at evaluation. Yeah.
Take into account sentence length, or do you end up with short sentences supporting other short sentences?
Right, this doesn't take into account sentence length, so it will treat the sentences regardless of length. Yeah, Eric?
Do you compute this by random walk?
Yes, by random walk.
So couldn't you avoid having a threshold by taking a walk proportional to the strength?
Oh yes, we have actually done this. We compared the exact same method without doing the binary step first, so we can compute page rank without having a binary matrix. And it turns out that we get the exact same result. That's a good question. So this is the sentence that will be picked by any of those methods, and those are the sentences that would be ranked second and third according to each of those methods, just for an illustration. Now let's see how we evaluate this. How many people here know about blue and rouge as evaluation metrics? Okay, so for those who don't know, those are two metrics which are not perfect, but which have been shown to reasonably well correlate with human judgments for machine translation, for text summarization, and for generation as well. And they're based on n-gram precision and n-gram recall. So in both cases, you have a target summary or target translation, or perhaps multiple target summaries and multiple target translations, and then your system is evaluated based on how similar your output is to the expected output, based on like a weighted sum of 1 grams, bigrams, trigrams, and so on. The difference between blue and rouge is that blue uses precision as the main metric, and rouge uses recall. And typically scores around 0.3 are considered quite good. Even though you could get much higher score, it turns out that even humans who compare their results against each other don't get anything higher than that. So this is a little comparison. It's a little hard to read those numbers, but I will give you the idea. So we have first a bunch of centroid-based methods on the duck data from 2004, by the way, which is like a very large set of clusters, with different values for the different centroid-based features. Then you have degree, which is just based on how many neighbors each page has. And finally, Lex PageRank, which is based on the cosine centrality. And here we have different evaluation methods, Rouge 1, Rouge 2, so those pay attention to different types of n-grams. And finally, we have Rouge W, which takes into account recall, but in terms of the longest common subsequence between the expected output and the system output. So what is important here is that we get numbers in a narrow band, but it is always the case that the degree-based methods, such as degree and Lex PageRank, outperform the best existing baseline. So centroid was the method that finished in first place in DUC last year. Okay, so we are now comparing against that and trying to get better performance. So we get Lex PageRank finishing the three highest ranks in this column are all associated with Lex PageRank. Similarly, the three highest scores in this column are all Lex PageRank, and finally here we have 2 degree and 1 Lex PageRank. Now the statistical significance is fairly low, and it only appears between the highest one and somewhere in the 10th position. So the first 8 or 9 are typically not statistically. I'll answer this question right away before somebody asks me. So it's not such a strong result. Now, so those are the official results from DUC in this year. We participated in several tasks, which are again a multi-document summarization. And here's the rank among somewhere between 15 and 22 systems participating that we had on the different evaluation metrics, the different tasks. So we finished in first place in most of the metrics for the tasks 3 and 4, which were multi-document summarization of either English documents or documents translated into English from a foreign language. And we didn't do so well on the last 2 metrics, which are based on longest common subsequence. So we finished somewhere between 2nd and 7th place among those. Okay, so a little conclusion for this part. So the summarization using CST, we use the relative utility evaluation method, which is a different evaluation. And we show that according to the human judges, summaries that use the CST connectivity method are actually better in terms of readability and faithfulness to the original at a very high statistical significance. And then I'll skip this part here. We have most recently been able to use the same technique for a web page summarization, for topical crawling. The idea is that you want to find pages that are similar to a given query, but instead of following links and reading entire documents, what we do is we just follow links to documents based on their summary. So we look at the summary of a document and we decide whether to follow that link or not. And we get the same accuracy for focus crawling as we get with full documents, even though our data processed is about a factor of 10 less. And here are some other ideas for recent projects that we have answer focus summaries, where you have to find the sentences that contain the answer to a question like how many people were killed or who was at fault and so on. And here just a little bit about the competition. So there are 2 other systems that do similar things to our news analysis. So ours was the first one in 2001, and then there are 2 more systems that do summarization. So there's one that you may have heard, Columbia's News Blast, a very nice system. And Google News, which goes all the way to clustering and putting together news from many different sources, but it doesn't do any summarization, at least as far as I know, or publicly they don't do that. So this is the end of the summarization part. Oh, sorry, there's one more thing, which we also have an interface for like web services with WAP-enabled devices. So this is the end of the first part of the talk. Now, if you want, I'm going to go on for about 15 more minutes and tell you about the other things that we're working on at Michigan. And I won't feel offended if you leave right now. But I would rather you keep listening. Any questions so far?
in the past evaluation, are all the systems multi-document summarization?
Okay, there are different tasks every year. And this year there were 4 out of the 5 tasks were multi-document summarization, and 1 was headline generation. In previous years there were also single document summaries. And we've done quite well on those as well. Question?
Can you do it somehow? I mean, with custom you can do completing information, right?
Right.
You choose the one that completes less if there are lots of counts. Or would that this cover that?
Oh, okay, yes, you're right. So one thing I forgot to mention is that in any of those algorithms you have so-called diversity-based re-ranking. So if 2 sentences that you're going to put in the summary are too similar to each other, you penalize one of them for being too similar, and then it may end up ranked lower, and you will pick one from a different cluster. So this takes into account cases where some of the input sentences are too similar. So this is based on an idea that first was published in 98 or 99 by Carbonell and Goldstein in SNGER, based on maximal marginal relevance. So the idea is that a sentence becomes less relevant, or less important for a summary, if another similar sentence is already in the summary. And the same method obviously applies to document retrieval, where if you have several documents that are all relevant, but they're too similar to each other, you lower their scores for the remaining one. Okay, so the next thing I want to go just very quickly, I want to spend about 1 or 2 minutes for each project to give an idea of what we've been working on. So one is a project that I was involved with last year with Franz Orr and a few other people. It was a Johns Hopkins workshop. We tried essentially to get a very good statistical-based machine translation system. And it is that typically statistical machine translation systems are based on the noisy channel model. We try to essentially uncover some string in another language based on the observation in another language. And it turns out that people who did well on those systems never used syntax. They thought that it was not possible to use it. So what we decided to do was to take, in the Chinese to English translation case, a given Chinese sentence, then we parse it with a parser for Chinese based on Dan Bickel's parser from UPenn. Then we take the 1,000 highest ranking sentences based on a syntax-free statistical method. We parse all of them, and then we compute a bunch of features. So again, we have the Chinese sentence here, 1,000 English ones. For each of the English ones, we say how likely is it that that sentence could be produced from the Chinese parse tree. And we look at things like, is the number of constituents of any given depth the same across languages? Is the English tree grammatical? Are the 2 sentences of comparable length and so on? So you have features that are bilingual, features that are monolingual, and finally features that are not syntactic at all. And then we use a greedy search algorithm trying to maximize the blue score of the translation. And we add 1 feature at a time. So we pick the feature that gives us the highest improvement in performance. We add it to the mix. We retrain the model. And then we get another one, and so on and so forth. And then it turns out that, okay, I'm going to skip some of this stuff, but at the end what happens is that we get from a baseline of 31.6 blue score, which is the highest available statistical translation result so far, to 32.9, which is statistically significant. But it turns out that most of the improvement from 31.6 to 32.9 actually came from a non-syntactic feature. It came from IBM Model 1. And then the syntactic features contributed the rest from 32.5 to 32.9. This is one of the projects. Another project is something called phylogenetic text modeling. Yes?
Didn't help much?
They helped, but not much. That's the conclusion. But the framework for adding features actually helped. It was very good. Okay, so the next thing, as I mentioned earlier, many techniques from bioinformatics have been used in natural language processing. And the idea is very simple. People who do phylogenetics deal with the evolutionary tree of different organisms, different species. So you have, for example, certain ape, and then the human, and so on. And you look at the sequence of DNA and you find mutations. So if 2 sequences are very similar, but they have 1 piece that's different, you assume that they come from the same ancestor, and at some point a mutation made them split apart. So what we decided to do was, just for fun, do machine translation identification. So here's how this works. You have a single sentence in Chinese, or in any other language. We did Chinese and Arabic. And then we look at the multiple translation corpus that was released by the LDC. So that corpus contains 17 translations of the exact same Chinese sentence, produced by different humans and different automatic systems. So there are actually 2 groups. Can you figure out which one is human and which one is automatic?
second one is human translation.
Right. So the second one is the human translation. The 11 are automatic, but you see, it takes you a little bit of time to figure it out. So what we wanted to do is, given those in a shuffled order, can we automatically figure out which ones are the manual translations and which ones are the automatic translations? In this case, what we do. We produce a phylogenetic tree, which is based on the edit distance between the different pairs. So the higher the edit distance, the less likely they are to come from the same part of the phylogenetic tree. So the way to read this is that sentences 14 and 15 are closest to each other. And there is a single parent, number 13, which is not a sentence. That's a new sequence, which is similar to sentences 14 and 15, from which, through a mutation, sentences 14 and 15 were generated. And then that new sentence is added to the mix, and then you find the second pair of most similar sentences, like this one here, and you keep repeating this until you get a sequence that goes to the root of the tree, at number 5. Okay, and then what turns out to happen is that always the sentences that are manual translations always cluster together. Okay, like here. So if you know even one of them, you can figure out what are the ones that are also manual translations. And we did a statistical analysis of this for Chinese and for Arabic, and we actually showed that except for 2 out of 200 cases, it can always tell the manual from the automatic translations using this method. Eric?
What is the intuition for how this works or why this works?
I mean, it's not very clear to me, in fact. You have to keep in mind that those humans are not related to each other. They're just the students, typically, who have been asked to translate those sentences. The machine translation systems use very different algorithms. They come from all over the world. And yet, it turns out that somehow because of, for example, the existence of certain phrases that are more natural, yeah, maybe Ken can...
Well, on the machine translation systems, they were probably trained on relatively few training corpora.
Right.
And they probably
They train
share
on the exact same training corpora, and they're mostly the exact same system.
So they're not trained on the same corpus at all.
This is not the closed task. This is well, I mean, there's the NIST has the closed corpora and the open corpora task, right?
No, this includes open corpus, so they're trained on very different
Clusters, the underful clusters.
Yes, go ahead.
Is this the unique? Usually you have problems with breaking ties.
Yeah, usually they're not unique, but we use like a reasonable tie-breaking mechanism, so we end up producing unique trees, and we're talking about those unique trees. I don't know if you use a slightly different tie-breaking mechanism. I don't think you would get a very different result. Yes.
Were the manual translations done by people who are primarily Chinese speakers who learned English as a second language?
I don't know for sure, but I believe that most were native Chinese speakers who spoke English as a second language.
So if they had a mix of primarily English speakers who learned Chinese as a second language, they may not cluster so well.
That is quite possible. I don't want to make a claim about that. Okay, now, let me show you one other place where phylogenetic algorithms are quite useful. And the first one was more for fun. You understand that this figure out which one is automatic, which one is manual is not such a great achievement after all. I mean, it's not something that you would like write home about. I think this one is more interesting. So we do the same thing now, but with the single language and with real sentences, not manual translation. So those are sentences from multi-document clusters, which come from the Musin system. And what we do is we figure out the timestamp for each of them manually, so we know that this was published at noon and 22 minutes on this date, and so on. Then we measure again the edit distances between them, and we build a phylogenetic tree, which tells us which sentence is most likely to be the root, and which ones are most likely to be the descendant. Now, one thing I need to warn you here is that the phylogenetic algorithms are rootless, meaning that they don't have, you don't know which node is the root. You always have to designate the root node, because you could really lift this structure by this node, and you would get a very different structure. You still preserve the inter-node distances, but the ordering will be different. So in this case, you have to know which sentence comes first. All the other ones come out automatically. And here's how you do this. You represent the intermediate nodes based on the distance to the real nodes with the sentences, and then you project based on the distance from the root on the time axis here. And you get sentence 1, sentence 2, sentence 3, sentence 4 in this particular order. And then you compare using Kendall's tau this ranking of the sentences against the real correct chronological ordering, and you get the accuracy of the algorithm, which is actually quite high. We get some Kendall's tau, which gives us very high statistical significance. And the best representation, by the way, is when you remove stop words, which is something that you would expect. Okay, so next thing. I'm going to try to finish in about 10 minutes. The next thing is, I'll skip this part. Actually, I know, let me talk about it very quick. So one of the things that we're trying to do now is time-based question answering. So you have questions whose answers change with time and over source. And the goal is for each of those questions to give the answer in the form of this chart. So this is the question, how many people were dead or were injured in that particular accident? You have the sources here on the x-axis and the times on the y-axis. And it turns out that very often you first obviously start with incorrect answers, and then after some time passes, everybody knows the correct answer to the question. So there's an ultimate final answer that you can compare against. So the question is, can you predict at some point in time, for example, based on prior training data, what's the probability that if the most recent answer to this question is this, that this will remain the correct answer within a certain number of hours in the future? So this is a new project that we don't have enough results to report on. Okay, the next thing is, very quickly, is about syntactic alignment. Now, people here may have heard about this paper last year, Barzilai and Lee in NACO 03. Have you? So the idea was this. For information retrieval and for other NLP tasks, it's very important to be able to find the two sentences are somehow similar. So they mean the same thing. So if you look at this example, John talked with Mary, and John had a chat with Mary. You would agree that those are fairly similar sentences. So for IR purposes, you may want to be able to ask this as the query and return this one. If you just look at the lexical similarity between those two, it may not be very high. In fact, any sentence that has John and Mary and any other word will be just as similar to those. So what Barzilai and Lee proposed to do was, again, to use a technique from bioinformatics, which is called sequence alignment, based on dynamic programming. So you take the two sentences, like this, and you represent them in a dynamic programming chart, like this. So this is the first sentence, this is the second sentence, and so on. And then you decide, again, based on the dynamic programming algorithm, what score to assign here and here and there and there. And finally, you can have a path that goes through the dynamic programming chart that tells you how to align those. And then you end up with a new automaton, which somehow represents the original sentences, but it can also allow you to produce novel sentences that were not seen before. So, for example, if you had this and also this, and this was one of the original paths, this was another one of the original paths, you would now be able to produce one of the crossover paths as a novel way to say the exact same thing. So what we decided to do is, well, let's see how we can use syntactic information to do the alignment better. So to decide that something is better, we have to have an evaluation metric. And in our case, there are two evaluation metrics. One is fidelity, and one is grammaticality. So what you want is a random sentence that will be generated by this new automaton to be first grammatical, and second, to not say things that cannot be inferred from the original sentence. When we compare this with the Barzilai and Lee method from last year. So here's how it works. So those are the input sentences. They come, again, from many different articles in the News in Essence collection. And we train our model. I'll explain how. And we get a new sentence that looks like this. So this is a sentence that was not in the original sentences at all. And yet, if you read it carefully, you recognize that it's grammatical. And yet it provides pretty much the same type of information as any of the original ones. So for IR purposes, you could use one of those as the query and retrieve all of the other ones, and vice versa. So the algorithm is described in the paper, but I will give you the basic idea. The basic idea is this. If you are comparing this here, let's say AI with BJ, where A is one of the sequences, B is the other sequence, when you compute the score here between AI and BJ, you give it the high score of alignment if they have the same word, but an even higher score if they have the same part of speech, and yet higher if they have the same local syntactic structure. So, for example, if the two are, let's say, prepositional phrases, heads of prepositional phrases, you get an even higher score than if they're just nouns than if they're just the same word. So once you get this, you can do the evaluation, and we did the following. We compared 3 lexical methods that don't use syntax with 2 syntactic methods, and we generate new sentences. And it turns out that the best of our method, which was syntactic alignment without considering stop words, using a large number of human judges, we got a grammaticality of 3.74 on a scale from 1 to 4. and fidelity of 3.77 on a scale from 1 to 4. This is compared with the best baseline, which is the Barzilai-Lee method, without using syntax, of grammaticality 3.12 and fidelity 3.07. I cannot do statistical analysis here because those are still subjective judgments and you don't know the distributions, but I believe that this is a fairly good indication. Just to give an idea of the qualitative scale, so 4 meant that it's a very grammatically correct sentence and it can be exactly derived from the original. 3 was that it has errors, 2 it has major errors, and 1 was it's nonsense. So we're going essentially from almost perfect to errors everywhere. Okay, so I'm going to skip this part. I'll just tell you that we've been working for quite many years on web-based question answering. And we have a system called Answer on the web that's been there for several years, where you can just type in a question like, where is Microsoft based, and they get the answer. And the reason I'm not talking more about this is because there are many people doing question answering these days, even here at Microsoft, like Eric, for example, have been working on this for several years. So one of the things that we're doing most recently in this world, however, is question modulation. So the idea is that we want to take a user question that looks like this: what country is the biggest producer of tungsten? And find a way to ask this question which gives us the best performance, meaning the best documents with the correct answers using the syntax of a particular search engine. And it turns out that in our case, we get a 42% increase using a genetic algorithm which uses the following evolutionary operators: mutation, permutation, and so on. So we get a TRDR, which is the metric used in tech for evaluating question answering systems. A 42% increase compared to sending the baseline, which is the original question as it is. And again, the idea is that you can learn essentially phrases. For example, biggest producer of tungsten, if it's sent with double quotes around it, would give you a higher probability of getting the right answers than if you just send them in no order at all. Okay, so another recent project is relation extraction. So the idea is that we get the user to type in examples of relations. For example, let it be is the first argument of the relation. The Beatles is the second argument of the relation. We give 5 or 6 examples like this, and then we go to Google and we search for sentences that contain those, and we try to find phrases that will link those two sentences, those two phrases together. And this way, we can extract more examples of the exact same relation. So this is a new project. We don't have a paper on it yet, but we're now trying different things like songs and singers, protein-to-protein interactions, organization leaders, and so on. And now the next thing, I'm going to skip this part completely, but we're working on a very large project on models of the web, where we're trying to predict the structure of the web based on the similarity between documents. So here's the idea. I'll just show you the last slide here. The idea is that you're more likely to create a link between 2 pages if they contain some similar content. For example, if they're both about sports or both about politics and so on. And the way to predict if they're the same topic is based on the occurrence of individual words. And we had a paper in HOT this year where we actually showed the probability, how the probability of 2 pages being linked depends on the presence of particular words in both pages. This is something that we call self-triggerability. So, here I don't claim that I'll explain what this is. If somebody's interested, I'll be available from 5 to 6 to tell you more about it. So I'm going to skip this part too. This is the HOT paper. And this is essentially what we're trying to get at. We're trying to predict what's the probability that 2 pages will be linked, given that they are of a certain length, they contain a certain number of words in common, and so on. And now there are 2 more things which I'm going to show you, which I think are worth looking at. One is a new method that we're trying to come up with for our text classification. And this is something that I would like to get feedback from you. Okay, so I would please ask you for questions afterwards. So here's the idea. When you do classification, you have objects that can belong to one of multiple classes. For example, an email could be spam or not spam, or a page could be a home page or not something else. Or in the case of more natural language problems, for example, word sense disambiguation, a certain instance of the word board, B-O-A-R-D, could be sense 1 or sense 2 or sense 3. So for classification purposes, people usually use a supervised method, so you have a lot of training data, and then you come up with certain rules that you apply on the unseen data, and you do some classification, and then you measure accuracy. More recently, people have started to look at unsupervised methods and weakly supervised methods, because it's not possible for every given task to come up with such an amount of training data. People are familiar with things like bootstrapping and core training and active learning. Actually, some of those originated in natural language. So there's a famous paper by David Jarowski from about 10 years ago, which for the first time introduced some of the core training ideas. So here's what happens. I'm just going to get to the point here. Suppose we have this sort of representation. So this is the new part. A bunch of labeled examples, but still very small number compared to the overall size of the corpus that needs to be labeled. So those could be, for example, all the pages that are known to be spam. And those are the unlabeled examples. So those are pages that are not known, whether they're spam or not. And then you have binary features. So the binary features are associated with particular instances of the labeled or unlabeled examples. So this feature here, for example, is true for both this and for this object. So you can actually have a joint distribution. So the f of this feature here, f1, comma, this particular labeled object is equal to 1. And the same thing for this one, and this one is 0. So the idea is that you want to label the unlabeled examples a certain color based on how similar they are to some non-labeled examples. And I'll give you an illustration from another paper by John Lafferty, which is was a very good motivation for ours. So in their case, what they do is this. You do OCR, and you have some known instances of different digits, like 0, 1s, and 2s. And then you have different observations. So, for example, this is one squiggle, and this is another one, and this is another one, and so on. And then you measure the similarity, for example, based on how many pixels those two have in common, or some very straightforward to measure metric. And you build a graph, which again has one where two things are thought to be similar to each other, and 0 where they're thought not to be similar. And then to classify something, what you do is that you want to classify this guy here. Well, how do you do this? You do a random walk, and then you figure out whether you're going to get first here, or there, or here. And the one where you get first is the one that you use as the label of your object. And obviously this will give you, based on the topology of the graph, some regions, like something like this, where everything that is closest to the 1 will be labeled as a 1, and so on and so forth. So the question is to do the partitioning based on the random walk. So let's go back to our example here. So let me give you an example of what features those might be. So this could be the word, let's say, board, B-O-A-R-D, in sentence 1 of the document. We want to label it as sense 1, sense 2, or sense 3. And we know that in this particular case it's sense 1. And let me say, for example, is the word on the left the word the? If it is the word the, then we link this feature, which is the word on the left is the, to this particular object. And we also link it to this one and to any of the other ones for which it holds. And then we do a random walk. I'll explain the left part in just a second, but the random walk works like this. You take the feature vector, which is the values of those features at previous iterations, so at the beginning they're all the same. And then you add to those the transpose of the connectivity matrix between the features and the labeled examples with the labeled examples. So you take the product of the transpose with the labeled examples, and you add this new information back to F. And then you're essentially propagating some labeled information from the L part to the F part. And then you're propagating similarly from F to the unlabeled examples and back to F. And then you could also potentially go back to L, but you don't need to because those are known to be labeled in a particular color. And you repeat this sequence of 3 steps iteratively until convergence. And then what happens at the end is that each of those nodes gets a score. And then you can decide, for example, based on some prior knowledge of the distribution of the different classes, what threshold to use to categorize a certain object as one color or as the other color. And typically what happens is that the closer you are to labeled examples, the more likely it is that you are labeled the same color. So you see, there's only 2 hops between this node and a non-labeled example. But there are 4 hops between this one and a non-labeled example. That's why the color of this one is whiter than that one here. So this, again, is something totally new, and we don't have enough results for it yet. And we actually, just to conclude this part, we're using this now on the problem of classification of numbers. For example, we have things like 300,000 to 1 million people, and the user question could be something like this. how much money does it cost to get to England. So how much money is consistent with a number type that is money rather than quantity, like in this case. So in this case, if we can tell that this is not a money, or rather a quantity, we can rule out this phrase as a possible answer. Okay, so the current results are pretty much only the following, that we're comparing spectral partitioning, which is another known method for bipartite graphs for classification, with tripartite updating, which is the name of this method. And we were able to handle twice as many labeled examples with 10 times as many labeled examples with the exact same accuracy as spectral partitioning. But that's still not as good as doing something like decision lists, which is something that we'll consider next. Okay, I'm going to skip this part. We'll try to pretty much get to the conclusion. So the big themes that we deal with are things like modeling, things like evolving information, identifying importance, dealing with redundancy, also dealing with link structure and textual data. And the people that I would like to mention, and the organizations that I would like to mention are NSF, NIH, ONR, and some of my students who have been working on this. In fact, Zhu Zhang was a summer intern here for 2 of the last 3 years. And UROP, which is the Undergraduate Research Opportunity Program at Michigan, which is very nice. There are about 4,000 students every year who are funded by it to work on particular research projects by the university. And I would like to mention also the Johns Hopkins workshops where some of this work was done, particularly the machine translation work. And there's some papers that I will point you to where all this is described. And finally, this is a slide that shows you how I view the future, if you wish, of this area. So this picture shows you the different problems that people have to deal with, like number classification, summarization, web models, machine translation, and so on. And then all of the research issues that have to be solved for this particular problem. So you can see that this graph is fairly dense, and many problems are always associated with many potential problems. In many research areas are associated with many problems. For example, multi-source appears as an issue pretty much everywhere, as does uneven importance or redundancy or graph structure. And similarly, some of the harder problems like summarization and machine translation all involve many of those issues that have to be resolved. Here I have a list of some interesting research projects that some of my students or I are currently working on. And, oops, sorry. If you're interested, again, I will send you the slides afterwards. And the next thing is some of the systems that we have built. So the first one is about question answering. Next one is about machine translation generation. The next few are about summarization and question answering, and so on. And that's pretty much the end of my talk. So I think I was able to finish on time, so I apologize if I had to skip some portions to do that. So thank you. Any questions? I'll be happy to answer. Yes, Luz.
All the way back to the beginning, with using Essence, you said you could provide summarization based on a user model.
Right.
Is the user model simply the seed document that the user...
No, the user model knows that it also contains the preferred sources of information, how much you should pay attention to redundancy, the expected length, the frequency of updates, and the relative weight of the different CSC relations. So there's a lot of information.
So the CSC relations are automatically identified.
Right.
Okay. That's something I'd like to talk to you about when we get to the class.
It's actually quite hard to do that, right? We had very good results. This was last year in CIKM. We had very good results.
So, for the tripartite graph.
Yeah.
So how is that different than, I understand in the bipartite situation you just have the stationary distribution on each side of the graph.
Right.
And here, the difference is that you know the values of some nodes, and you just fix those, and you could let the same algorithm run.
Right,
like
correct.
in any sort of way. This is what you know, and this is what you don't know. Is that correct?
Yes, that's correct. So there's actually one of the motivations of this is that in the CMU papers, like the John Lafferty's papers, they use a model called the Ising model, ISING, which comes from crystal structures of crystal structures of solid state physics. And in that case, there's a special case of this Ising model called the pinned Ising model, where some states are not allowed to change. And people have shown that those methods actually work quite well in modeling, crystallic structures, whereas in our case, it was not a major difference between the two. So I don't know if there's any. What I'm really trying to say is that if you let those original values change, the ones that are labeled, you get worse performance. So we are really encouraged to use the one that are stuck. That one we didn't explain as well, but the idea is that you shouldn't allow the things that you know for sure, you don't let them change. Like in an EM model, if you know certain values of the probabilistic model, you just leave them alone. Yes.
What paper did you describe the work on paraphrasing using syntax?
Okay, so the original paper was with Barzilai and Lee in NACO 03. Our paper was in IJCNOP 04.
Okay, well, thanks again.
Okay.